Time. Wow, the class shrunk by more than a half. It's week 8. We're not quite done yet. Almost done, but not quite done yet. Was the traffic bad? Oh, okay.
It's not like this is law school.
Huh?
I said it's not like this is law school.
Oh. All right. Well, we'll go ahead and get started. It's after 6, so we'll just move forward. Okay. No, there's a homework due. Oh, you can't see anything. That's not good. Be helpful if you can see what I see. So this is compilers week 8. We have 2 more weeks. So we're going to look at the schedule and see what's coming up and what else we still need to cover. So mostly I'm going to concentrate on what you need for the project tonight. And then if we don't get done tonight, next week, and that's really should be working on. Okay, so I still can't see it. Hang on. So your lab 2, part 2 is due tonight. So is homework 4, and that's really the last of the homework and labs. All we have left is the project at the end. Oh, it's really slow tonight. Everything is slow tonight. Yikes. Okay, there you go. Okay, so I know I've gotten a few questions on homework 4 already. So I actually have a couple more examples I'd like to go through. And then if you still have questions, we'll answer those. And that's the L1 parser. And I managed to mess up my Visual Studios on my laptop. So it doesn't even do Hello World anymore. So, huh? What happened? Do you know how to?
I told you about on Saturday that mine just totally whacked out.
Yeah. What did you have to do? Wipe everything out?
I removed Visual Studio and loaded it, and then painfully reinstalled it after.
And then that fixed it?
Trial and error.
Yeah.
I just deleted stuff randomly.
Oh dear. Okay. All right. So I do have a L1 demo I'd like to show you. So if I don't get it on my laptop, I'll try it on this lab machine over break and see. So I've been working on this most of the afternoon, trying to get this thing to work, but who knows? It's Visual Studio. So we'll just go back to the previous version, whatever. Okay. So I'd like to see tonight at least compare the top-down parser versus the bottom-up parser, and then show you a tool. I think it's pretty cool. Basically, you just gave it the grammar. It goes through and parses the grammar, right? The grammar rules themselves. So there's a parser there too. It's like a parser for a parser, right? So it's like compiler of a compiler kind of thing. So it's called a compiler generator. So what happens is it parses through the grammar and makes sure the grammar is correct. And then based on the grammar, it generates a table. In this case, is SLR table, LALR table, not LL1 table. It'll be nice if we can generate the LL1 table, but I'm sure there are tools out there that could do that. Or you could write one, so you're one of the project options. And it actually shows you how to, and then it generates a tokenizer, the DFA, deterministic finite automata, based on the grammar. Right? I don't even have to tell it what are the token types. It figures out what the token types are based on what you have in the grammar, right? Because we're sort of like the whole, right, the path getting to the parser. We've already done the tokenizer. We already figured out what are the tokens. But actually, everything could be just in the grammar itself. Okay, these are all the tokens. Go generate a tokenizer. And the tool does do that. It goes off and generates a tokenizer. And then it has a little simulator window where I can just type, enter some sample code, in this case, C. And then it goes through and show me actually what are the tokens, how it goes about figuring out the syntax step by step. It builds for me a parse tree, I think I can show you. and which is your homework one. Think back, way back, homework one. You had a Pascal grammar, you had this program, and then you were supposed to write a tree for it. Well, the tool could do that. Basically, took your sample input, took the grammar, and builds a tree. And you will need some kind of a data structure for some of the project options. You need somehow save that information because you don't want to go through and parse this the whole thing again. So if you already gone through the parse, you determine, okay, I got this type of statement, I got, this type of loop, I got this, all these stuff. Well, you can just save it somewhere internally in your data structure. Then you can go through that information and do analysis, do code conversion, do generate GUI, whatever it is you're supposed to do with your result of your parse. But whatever it is, right, it needs to be saved somehow so you can actually get to it. So I'll talk a little bit about that. And I think there's some miscellaneous topics I like to cover. So it's a lot of words on that slide. Okay, so today we're just going to kind of, continue with that all one and then talk about the bottom-up parser. You really should start on your project or find a partner if you're going to team up with someone. Start thinking about it tonight and get your labs done. Yes, but you should be thinking about that. Week 9, if we don't get done tonight, I'd like to wrap up some miscellaneous topics. Really, week 9 is you should work on your project. Okay, I will be here, answer questions. We'll have another test on week 10, the last day of class. I'll post the checklist like I've always do, and you should continue to work on the project. Because it's the last day of class, we always have pizza, so that's week 10. And then finals week. Your project is due on Monday. I'm going to be here on Monday night. If you're here, I could check you off. If you're not here, you can still turn that in, but make sure you give me detailed instructions on how to run it. If there's anything special I need to do to make your program run. Otherwise, I won't be here to check you off. I'd like to see your project and check you off. If you get it done by Monday, the 14th, I think it's 14th, yeah, 14th. If you have any late assignments, labs, projects you want to still turn in for this term to be graded this term, I need that by Wednesday so I have time to get them graded, right, and then get the grades in. And for compilers class, it's kind of automatic because this class only comes around once a year. And I know sometimes you just don't get the project or the lab done. You get it incomplete if if you don't have all the labs and project in. And then and I know you want to work on it over spring break. The reality is you're probably not going to work on it over spring break. Okay, spring break is short, but you have actually till end of spring term to get the labs and project in to get a grade. The success rate of incompletes and compilers, the people that actually finish, actually get the incompletes removed, is like 5%. Okay, so the reality is when you leave here, you're probably not going to get it done. Unless you really determine, you're going to get out the door in June, you have to get your diploma, you are going to get it done. Well, I could help you. I have students say, well, I'm going to check in with you every single week in spring term until I get this thing done. That's fine. I'm doing that with my seniors as well. If they're saying, I really need to see you more than once sprint, right? I need to see you every week so I can get this on track. I have a senior coming back after 10 years. He graduated, well, he thought he graduated in 2005, but he's still missing 2 credits of senior project that he never finished. So he's back, and I'm seeing him every week. So please, if you at all possible, even if you did a horrible job, okay, get this done this term so you don't have to worry about it, okay? Yeah, one of my seniors is actually the very first compilers class here. I've taught this for years, but he actually did get it done like end of summer. So he came back and show it to me. That's fine. As long as you get it done within a year, I can still change your grade. But when this thing comes around again next year and you still don't have it done, you have to retake it. Okay, that's the rule. So don't get yourself in that position if at all possible.
What are really good office hours to check in with you, Sheriff?
I'm here on Mondays.
Okay. How many Mondays?
I'm usually here all afternoon on Mondays, Tuesdays, and Saturdays, and the other days as needed. So
So
tomorrow,
Monday, Tuesday, and Saturday.
Saturday, yep, in lab is a good time. I
So
usually don't get a lot. 2 to 5 is my lab. I usually don't have a lot of people here on Saturday, so that's a good time. Tomorrow afternoon, actually, I'm going to Corvallis to talk with some students. So I'm recruiting some students. So tomorrow, and if you want to just chat with me, I can do Hangout, Skype also. So you don't actually physically have to be here to talk to me.
Time to try to reach you on Hangouts.
Just email me.
Oh, email.
Yeah, email me. Yeah, we'll set up a time. Yeah, I'm usually available a lot.
Thanks for being online all the time.
Oh, I'm on I'm online all the
You made
time.
yourself very available to us.
Okay, okay. Okay, so I have a very simple grammar. I have one rule, one S, one noun-terminal, has two rules, A, S, C, and then B. Okay, so I'd like you to construct a LL1 table for me. You can probably just do it by looking at it in this case, right? This is very simple. I have two rules, one that starts with A, one that starts with B. Okay, I have no lambdas, so I don't even need to worry about a follow set. I could compute the follow set if I wanted. I can go through my 4 cases. Okay, so a caution about a follow set. Sometimes we like to reason, to look at it and try to reason what a follow set should be. Oh, if you have S here, therefore, okay, then you have, okay, then therefore it must mean, okay, so you try to reason just by looking at the rules. And sometimes those rules could get you in trouble, especially if it's really the first set, not the last, not the follow set. And the example, find a pen around here. So example is in one of the homework, well, several places in the homework problems, you might have something like this. Okay. The only information this gives you is the first set, D. But many of you say, oh, wait, this one really is recursive. So D must also follow D because you have another Y here. You have one D, then you have another Y. So, okay, so D must also follow Y. It doesn't. D is the first set. I don't know what follows Y based on this one rule. If it's not the first, if it's not the star symbol. Okay, because if you look at the parse tree, Y, jeez, it's terrible. Y, dy, okay, eventually may go to lambda, okay, or go to something else, I don't know, okay. I still don't know what follows Y. All I know is it starts with a D. I got a bunch of D's here. Okay, what follows Y is what comes after Y. Right now, it doesn't have anything here in this subtree. So usually what I have to do is I have to go up. How do I get to Y here? Okay, so I have this Y here that has a bunch of D's down here, okay? What follows Y, I don't really know based on this rule, but if I look up, how did I get to this Y? Okay, maybe it was that. Okay, if that's the case, then this B follows Y. Okay, B follows every single one of those Y's. Okay, this is the whole subtree down there. When you're done with that whole subtree, what do you have? You have maybe a B. I don't know. I'm just making up rules as I come up here. Okay, but just based on this rule though, it doesn't give me any follow information. Just the first set. Yes, Y is recursive. That's fine. It just means you're going to give me more first sets. It doesn't tell me what happens when I'm done with Y. I have to look elsewhere to see what happens when I'm done with Y. Okay, so that's the caution. Sometimes you try to put that, factor that information in and goes, oh, I have more D's, so it must follow. It doesn't. Okay, so caution. And just based on this, the follow set. Now I've discovered the laser. Like it. So the follow set, the first set is the first column. Simple. No lambdas, no big letters, A or B. The follow set for S, 4 cases. Case 1, when you're done with S, you have nothing left, $sign. Okay? Which in this case, not even going to consider, there's no lambdas here. Out of A, B, C, the second case is this SC, so C follows S, right? Okay, and there's no other follow set. I don't have big letters. I don't have big letters all the way at the end. I don't have them right next to each other. So that's it. That's really the first set is AB, follow set is C, which $sign, which I'm not going to use. There's no lambdas. It's really the first set, right? When we put things into a table, we always put the tokens across the top. In this case, it should have, I'm running out of space. It should have A, B, C, and $sign. But C and $sign are so not interesting because you can't start with a C. You can't just end with nothing. So I didn't run out of rooms. I didn't even put them in. So my table is just really just A and B. I have 2 first sets, 2 rules, and they plop down in the right place. So how do I know they're in the right place? A, B, B. If the first token doesn't line up, you put them in the wrong place. Okay. Not the first token. If I take S and grab a B, I should take that rule. If I take S and grab A, I should have that rule. Okay, it's very straightforward. I'm simplify it like the simplest example possible. And then part of the homework is, okay, now I have a table. I'm going to parse something with it. And if I ever get my program to run, I can show you. I actually wrote a program that read in this table as input, which has the grammar rules in there already. So essentially it took the grammar in as input, right, at that table. So SA, SB, right, and then what happens. And then takes this in as input, and then try to see how to parse with it. Okay, so how to parse with it is I need a stack. This is the data structure stack. It's my stack class. I wrote a stack class, C++ stack class. Has push and pop and all that good stuff, right? So I'm going to push S onto the stack. That's because it's top-down parser. I'm going to start with S, and I should have match everything with it. So I put S on the stack, and then this top of the stack, beginning of the input is my index into the table. Top of the stack, S, beginning of input is A, SA, I get ASC. Okay, so it tells me I need to pop off the S, replaces this S with ASC. Notice I pop them on, push on, and reverse. So the A shows up first, leftmost. A is the leftmost symbol. LL, the L means is I'm going to handle the leftmost first. So ASC, and I'll keep going. And you can do this in a tree form. You can do this in a tabular form as I have. You know, here's the stack, here's the input, here's what happens, stack, input, what happens. Or you can just show the stack each step. So ASC, what's on the top of the stack is A, beginning of input is A, and they match. And the only way they match is that if they're both tokens, since I don't have anything but tokens in my input. So I don't even have to check to see if there are tokens. There are tokens. Otherwise, they will not match. If they're the same token, I remove them. If there's a different token, you flag an error. This parser just stops. If I'm expecting an A here, you gave me something else. First of all, I probably won't even get to that point if you gave me something else. If you gave me a C as the first token, immediately my table will fail. There's no C, there's no SC, okay? But if somehow through this parser, parse process, I'm still ending up with a wrong token, then parser stops. You can't remove it unless they're the same. But if they're the same, okay, we remove it. I'll get SC left. And then do the same thing. I have another A, right? I remove it from the inputs. I have A, B, C, C. So I do another A. And notice on this A, this S, I pop this S. I still have a C left on the stack. This is how I keep track of the begin and end. A, C, A, C, A, C, A, C. Because it's left on the stack. This is a push down automata. I'm going to pop off the S and put ASC on there. And then do the same thing. The A's cancel out. Then I'll just have SCC. Okay, now I have SB, which then I'll get the B on there. The B's cancel out, the C's cancel out, the C's cancel out. The $ denotes the end. The stack, it will be empty by then if everything cancels out. The input should be empty if this BCC matches this BCC. Okay, so nothing left on the input, I'm done. If there's something left on the stack, something left in the input, or vice versa, you're not done. You got too many stuff or not enough stuff. Okay, so it's very simple parser. Algorithm-wise, it's a big while loop. Checks the table, checks the stack, checks the input, checks the table. Pop off something, push down something. Sometimes just remove, pop off on both. Okay, just keeps going until you run out of stuff, then you're done. There's no backtracking. Or if this was the wrong rule, if there was 2 rules that starts with B, you can't. It's 1, LL1. Every single token has 1 rule. There are LL2 parsers. It does not mean that every token has 2 rules. It means every 2 tokens has 1 rule. Okay, so the LL2 parser, which is a little harder to construct table for, means you look at 2 tokens at a time. Okay, I may have the B as the common token, but maybe it's BC and BD. Okay, the BC and BD will determine which rule gets picked. Then you can expand. How about LL3, LL5, LL10? There is a general LLK grammar, and that just makes the whoever has to write one of these parser tables, it just sort of, when it gets up to there, it's just really hard to see what's going on. So usually the most efficient way is to do an LL1 if the grammar is LL1. Some grammars are not LL1. So in your homework, 3 out of 4 grammars are not LL1. Okay, so, and it's not on purpose. I'm just making grammar up because I made them up, or some of them just turn out to be not LL1. Okay, so another way to think about this whole parsing process is that you'll say, well, what does this have to do with parsing? Well, it really is a table, right? It really is. So you start with S, is top down, and then which rule you're going to pick first? Well, based on the table, SA, you pick ASC. Okay, and then this A matches with this A, so it cancels out. This is my input. Okay, and then this S, we'll do it again. We have ASC. Okay, again, this A and that A cancels out. I have a feeling that the laser doesn't show up in the video. Oh, cute. Okay, so I have no idea what I'm talking about then. All right, well, anyway. And this S goes to B, and then finally the C's match up, right? That's exactly what we did with the stacks. But it really is a parse tree. So had I saved this as a tree, this form, instead of just going through the stacks. Or as I was going through the stacks, I save it as a tree, then I'll have all the information I need. Yes, I just parse through A, A, B, C, C, but I also have everything. So if these A, A, B, C, C's mean something, like their curly brackets or their special type of tokens or something, I have it. They're in my tree. So if I save some kind of structure as I was parsing through this, then I can go through this and go, oh, okay, let's see how many levels deep. Um, let's take all the A's and change that to something else. Okay, I have all the information there. I don't have to go back through the parser again. Okay, so that's really the result of parsing, is you have some kind of a syntactical structure. Okay, and how you save this syntactical structure really depends on how you're going to use this information later. Okay, so if this is a real grammar, I have meaningful keywords in here. I have meaningful information in here, assignment statements, and if statements, and while loop, and everything else. Well, I have them all in my structure. So I can go back through it again, just navigating through my internal data structure. Internal data structure. Doesn't have to go to file, doesn't have to go to anywhere else. It's all there. Then I can do something with it, this information. Okay, so that's really kind of what this any parser will do. And the fact that this is top down means we started with S. We start from the top. And then one token, one rule. One token, one rule. So A's and the B. We graph 3 rules, and that happens to match what I have. So anytime there's something that doesn't match, well, the table will tell me it doesn't match. What's on the stack doesn't match what I have in my input. Okay, just one more one example, then we'll move on. But this one, first of all, it has a lambda. It doesn't mean you can only compute the follow set for y. Okay? It means you actually have to compute the follow set for all of them, because the other sets may impact y. So other sets may actually impact y. Okay, so let me take a look at this real quick and see if it's LL1. Again, I just made this up. Okay, so at the first glance, it looks like it is LL1, but we'll see what happens if we get a table. And if the table doesn't fit, then we know, okay, it's not. Okay, so there are first sets, notice this open print is a token, so it's a first set token. It has a big letter. Okay, so this is a situation where you not only have only tokens in that first column, but you also have X, which means you got to consider what X is. That's the first set of S. X does not go to lambda, fortunately, so you don't have to go to the second column. Right? It's just that very first column, that's your first set, including this lambda here. And then as you consider the follow set, S is the start, so case 1. Here is case 2. Here is case 2. The Y is followed by Z. Y is followed by open right print. That's also a token. Okay, I know I threw it you probably on the homework. You didn't consider that to be a token. This is just like a little letter. It's a token. Right. Case 3, we have big X, big Y. Right, 2 big letters together. Case 4, X, Y. Right, so Y, Y, okay, Y is not interesting because it just goes to itself. But X, Y, that's the case 4. So I have all 4 cases in this grammar. And the first set is simplified by the fact that the first column doesn't have any lambdas, so just consider the first. So if you could just quickly do a first and follow set and put that into a table, we'll put it on, someone could put it on the board and we'll see what we have. Actually, I'll get the columns going and then you can put on the board to see what we have. All right. So we have three non-terminals, S, X, and Y. So it's S, X, and Y. All right. And the tokens are Z, B, C, left paren, right paren, and dollar sign. Okay. So if I said construct me a table, on the test will be close, probably close to your homework where I actually gave you the first and follow set. Actually, on the test will be, unlike your homework where you had to come up with the first and follow set and the table, on the test will be broken down. Here's your grammar, give me the first and follow set. Here's another grammar with this first and follow set. Show me what the table looks like. Here's yet another table. Let's show me how the parse works. Here's a string. Show me how it fits with the table. So it'll be three separate steps rather than lumped together. Okay. But anyway, here's the structure of a table. If you were given, if you had the first and follow set, you need to fill in the table. I probably will give you the table heading too, but so there's the heading. So let's take a few minutes to get that done. And then this is pretty much what you had to do for the homework if you're still working on it. Am I doing on time? Oh, perfect. Okay. And then we'll move on from the top down to the bottom up and some other stuff tonight. I will still take questions on homework 4. So catch me during break, or if it's something interesting for the whole class, we can do that too. But okay. Jeez. So I'll get a first and follow set up there too. So follow set of yep. I think that's what I have.
Bunch of a Z on
Wait,
X. One at the Z after X because the Y is lambda out S.
There's
Because Y has lambda.
there's an issue, right? So X goes to. Ooh, okay. So this might be one of those that's not LL1.
Oh How do you say that?
Okay, so x goes to
Which part are you trying to figure out?
x goes to beat y.
Yeah.
So anything that follows x also follows y. And what follows x is CB and Z. So the CB also gets copied into y.
That's right.
And then y actually has a lambda in there, so we have an issue there. And why did that manifest? Okay, let me see why that is the case. Huh.
We just totally broke it.
That's the case.
Really big.
So your beak is
Scratch that lambda. Fixes it.
so if B and C follows X. Oh, what? No. So this the Y B is the one that gets in trouble, right?
So C.
Okay, so
C
and
gets-
so C
C gets in trouble too.
C gets in trouble too. Okay.
You just toss that CB on there, they both get in
See
trouble.
why that is. Oh, right. Okay. So because both of them starts with that B. So if I could continue the B here, or make this lambda, or I can make this lambda and continue the B there. Yeah, that's the issue. Because just looking at it, it's kind of hard to see.
Want me to put that up? Or do you wanna
Yeah, you
just
want
text
to put that up? Yeah, sure. Go ahead. Yeah, thank you.
Before I draw my laptop.
Before you drop your laptop, okay.
Before I draw on it.
Oh,
I try
okay.
to,
Oh, okay. Yeah, you don't. Okay. So it turns out it's not LL1. It looks like it might be LL1, but it's actually not LL1. So that's kind of tricky. There's an easy fix to the grammar. Just get rid of the XYZ, make it XZ, then it's fine. But
So you can just drop the lambda.
you can drop, I think I still need a lambda at some point, otherwise the Y doesn't have a terminate.
Oh.
So, yeah, so there's an extra Y there. That's why it's not LL1. While David's doing that, I'm actually going to put a solution up in the slides for anyone who's actually watching the screen too. Thank you. Okay, if anyone watching the slides might be.
Is there
Okay. Okay. Thank you.
Parenthesis here.
Okay. Right, okay. So we have the first, and you can't see my screen. Okay, great, cute. Okay, hang on. I'm just gonna type in the follow sign. And I'll put it on the screen so you can see. Oh, come on. Okay, so let's take a look at the first set. It's pretty straightforward, I think. Let me make sure that we got the same thing. Okay, so first set, B, X is just B and the left print, the open print. Y is C, B, and the lambda. X, S goes to X. X doesn't have lambda, so it's just whatever X is, which is B, and the open print. So the first set is pretty straightforward. And then if we put stuff into the table based on the first set, and which is what David did. So thanks, David. Random, they're putting stuff on the board for us. Sure enough, S has one rule. Oh, here's another thing. S has one rule. Okay, we're not changing the rules. We're not making up new rules up. We're taking the original rules and put them into a table. Even though the first set is B, S does not go to B directly. Okay, so that was a common mistake on the homework. You're trying to put S going to BY. No, S just goes to XYZ. That's it. Okay. Eventually goes to BY or open print or something else. But right now it just goes to XYZ. That's the only rule it has. You take the original rules and put them into the table. Here's what we did here. SB, S open print gets XYZ. Okay. Two first sets, one rule, they both get that rule. If you have two first sets, two rules, figure out which one goes with which tokens. If you have two first set tokens and three rules, you're in trouble. There's not enough space. Okay, then it's not LL1. It's pretty simple. X, same thing. X has two rules, BY and open print Y, close print. So B and the open print Y, close print. Right? So they go in that column. And Y has three rules. We'll take care of the first set first, the B and the C. So the B goes with B and the C goes with the C. Okay? Then we have the lambda for Y. That's when we go to the follow set. But how did we compute the follow set? Well, first of all, case 1 gives us S $, because when you're done with S, you're done. Case 2, case 2, this Y has a Z following it. So the Z gets added there for the follow set of Y. because y could drop out. Okay, this y could just drop out. So you also get the z following x. Okay, see that? So that's why the z's show up twice for the x and y, because the y can drop out, then you just have xz. So z following x, that's for the lambda. Every time you have lambda, some of those lambda terms can go away, so check for that. Okay. And also y has this, the right print, the closing print. So that goes into the follow set. Okay, most people probably just stop here and goes, oh yeah, I caught everything. Okay, but we have one more, and that's case 4. X, Y, X, Y. So everything in X gets copied into Y. So I have a Z and the close print from case 2. I have case 3, I forgot. Case 3. X, Y. Big X, big Y. What's Y? B and C. So B and C follows X. No, we never copy lambda anywhere. Lambda doesn't usually get copied in the first set. Lambda doesn't usually get, there are no lambdas in the follow set at all. So lambdas usually don't get copied, even though Y's first set has a lambda in it. So B and C follows X. Anything follows X also follows Y. So ZBC gets copied in. Okay. Then my Y's follow set has 4 tokens. All 4 of those get lambdas. Great question. We don't copy lambda in the first set. So say if X had a lambda, and we're trying to compute what the S's first set is, we don't automatically put lambdas in there. However, if Y, in this case, has a lambda by itself, remember it's that first column? So when we take the first column, we do put lambdas in the first set. Okay? So if Y itself just goes to lambda, yeah, lambda is in there. Oh, the follow set has no lambda because we're it needs to. First set has to have lambdas. If first set does not have any lambdas, like this doesn't exist. First of all, it doesn't terminate. But if this doesn't exist, I don't need to compute the follow set. I'm never going to use the follow set. Right? I'm only using the follow set if the first set had a lambda in it. In this case, Y has a lambda. X and S do not. They do not have lambda.
First set, you mean Y or X also?
By the first set, I mean this first column. What's the first token? What's the first token you're going to see? Okay, tell me. I'm looking for S. What's the first token you're going to see? That first column. Right? Yeah. X and Y. We do the same thing. That's what I mean by first set. The very first token you're going to see. Okay? Yeah, follow means, what if Y doesn't exist? What if this Y is lambda? It's nothing, right? Lambda is nothing. So I'm looking for tokens. Well, how do I match nothing? This Y here. If this Y doesn't exist, just drops out. What should I see instead? I should see a Z. Because Z is there and then I'm good. Okay, why are you gonna drop out? Because I have a Z. Or if I see this, oh, that's okay. Yeah, why you can drop out? Because now I have a close print to keep going, right? But if you have something else, if you have, actually in this case, you have all of them, right? They're all there. Oh, how about open print, right? Yeah, I don't want it to go to lambda because the open print doesn't, it's not supposed. If Y to drop out, I will still never get to here because it's not in its follow set. So I'm only concerned about what should follow Y when I'm done, right? And it turns out all 4 of these could follow, then hence the problem. We got a problem here. This cell is a little crowded. So is this one. Well, actually, B and C. B and C. Okay, so both those cells are a little crowded. So this says, okay, I'm looking for Y, and I see B. I can either take the lambda, have it drop out, or I'll just continue to get more B's. And the reason for that, and the same with the C, the reason for that is X going to X, Y, Z, X going to Y, B, Y. So what if I just have, what if I have another B here? Is it this one, this way? Or is it what if I have a 2 B's? One way is to say, okay, have X grab the first B, making a lambda, have Y grab the second B, or have X grab both B's, then this Y can just be lambda. Okay, well, that's what this table is telling me. I grabbed 1B already because I banged, right? It came from X. But now, what do? Do I say, oh, no more? Or do I keep going, right? If I say no more, it's the first tree. If I keep going, it's the second tree. It's ambiguous. There's an easy fix. I just drop off the Y altogether. If I make S going to XZ, I think I'm getting the same grammar. I don't have the ambiguity because I still need to have an X. X doesn't go to lambda. So the Y is really just an extra. And X could go to Y, so I really don't need that Y there, I think. But sometimes fixing ambiguities is not that easy. It's just not, okay? Yeah, so I think if we fix this, if we just make this S going to XZ, and the X itself goes to Y, so I think that might work. But, I didn't play with it. I just thought, just by looking at it, right? Sometimes just by looking at it, I didn't catch the LL1 error either. So sometimes just by looking at it might not be enough. You have to do your first and follow set. Then you can see, just based on your first and follow set, remember last time I said, if you have a lambda here, you have a B here and a B there, it's not LL1. If you have a lambda here, you have a C there and a C in the first and follow set and a lambda, it's not LL1. You don't have to put in the table. Because when you do put it into the table, there are two rules per cell, 2 rules per cell. Okay, so just getting to the first and follow, you can probably see that it's not going to be LL1. In your homework, you have something very similar to this. Test 2 will have something kind of similar to this, right?
Actually, would the close parentheses follow the Y as well?
Did I have that on there?
Never mind.
Oh, I know it's kind of get buried there. Yeah, it's right there. Yeah, I know it's kind of hard to see. I've got my curly braces there. Yeah, you're right. Because there are 2 tokens, and that's case 2. 2 tokens, right, following the Y. Okay, so if you're still working on homework 4, you want to see me afterwards, during the break, you can ask questions, that's fine. I just want to kind of revisit this map and kind of show you where your project actually lands. And then when we come back from the break, I actually want to talk a little bit about bottom-up parser and then maybe take apart some of these information. And you may not need all of this information depending on which option you pick. So we've done the preprocessor, the tokenizer, the symbol table, and we did our lab 2 was really the parser. Okay, had I assigned lab 3, it would have been the LL1 parser because we simply run out of time to do that. Um, so lab 2 was a parser. What came out of the parser for you, what I asked you to do was basically yes or no. Yeah, it parsed. No, it didn't. Maybe with some meaningful error messages. Also utilizing the symbol table. Yep, X was declared before I used it. Right. So simple errors like that, you can use the symbol table to help you out. But what should come out of the parser as the product, right, comes the output from it is what I call the syntactical structure, which is really this parse tree, okay, or this data structure that represents what did I just parse? Yes, I wrote it out. Data declaration, function declaration, if statement, while loop. Okay, I saw all of those. But what you should, right, for the project, you may need to do that for some of the options, is to save that. It's not enough to say, yep, that was a data declaration, but what was it? But you say, well, wait, that's already in the symbol table. Data declarations went in there, right? That's fine. Data declarations don't necessarily have to be saved in the tree if it's already in there, but we're still dealing with the scope. So I want to see when they're declared, what scope number. So I may still need that information if int x is declared a bunch of times, or where, right? So I'm still processing like one, like, right, one scope at a time. So I may need to do that to actually, it's not enough to say, yeah, it's in a simple table, but okay, where am I using it? So I may still need to save that into a tree, and all of the statements should go into a tree. And that usually goes through the next phase, what's called a semantic analysis. Semantics is meaning, syntax is what it looks like. What does it look like? It looks like an assignment statement. Expression equals ID equals expression, semicolon. Semantic analysis says, the fact that we say, okay, has ID been declared is really semantics, right? It's the meaning of the language. Some languages don't care. You don't have to declare anything, you just use it. In fact, the type changes. If you say x equals 1, okay, x must be int. If you turn around and say x equals quote something, hello, oh, x must now be a string. Okay, that's called dynamic type. What we're doing is really static, as we're analyzing everything. Like say on paper is static, right? So you printed out your program, you analyze that, that's static. Well, that's really what compiler is doing. Right, here's your program, .cpp file, analyze it. I haven't gone into the executable yet, so I'm not running anything. Okay, so semantic type checking is part of semantic analysis. What comes out of semantic analysis is usually something called the intermediate representation. This representation could be a simplified tree. Remember your homework 1, that tree was huge, but it has stuff in there like semicolons and commas and all the stuff in there. Well, I don't need that anymore. I just need to know, what do I have? I have a loop. I have this type of statement. I have this arithmetic expression. I have this calculation I need to do. I have this output. I have this function call. That's it. Simplify it. Right? So there's something called the abstract syntax tree, which says, yeah, let's take the syntax, but let's take away all the punctuation marks, symbols. We don't need that. It doesn't change. I know, yeah, it works now. I don't have to worry about you're missing a semicolon because I checked it. I don't need to save that into a tree. I just need to save the meaning of what you did. And the intermediate representation could be a language. Microsoft's intermediate language is an intermediate representation. Okay? It could be another language. Well, if it's not a language, that means you have to parse it again. It's easier than your original language, but still, it's a language. You have to parse it again. Language has a syntax, right? Which means there's going to be another parser somewhere sitting in there. to make this happen. So compiler is really just a bunch of mini little parsers, right, along the way. We had a tokenizer, which parses out the tokens. We took the tokens, we feed it into the syntax parser. We feed it into the meaning, right, semantic analysis. Then we may get another representation out that I have to go parse again, but hopefully it's easier. Even in the code generation, assembler. If you produce assembly language and then you have to parse the assembly language to actually make an executable, assembler is a parser. What does it have to do? It has to parse assembly. How does it parse assembly? It has to know the assembly's grammar in order to parse assembly, which is easier than C, higher level language, but still, it's a parser. It's just a bunch of little parsers, like all working together. Okay, so that's really the big picture. We're not going to get to the optimizer. That's usually advanced compilers class, which at least at OIT it hasn't been taught ever. Assembler, linker, loader, how that works. That's advanced compilers. But really, we're more interested in the front end. I think the front end is a lot more use. There are some more applications for the front end. I mean, I could be writing little parsers all the time for whatever I'm doing. So really, this through semantic analysis, that's our front end. And we're in the project, we're going to add a little bit of back end, whatever you choose to do. The GUI simulator, that's the back end, right? You already parsed through the language. Okay, now go do something. So I think a back end is, okay, now I know what I have. Okay, what do I do? Go do something. Go do something useful with this information. Okay, that's really the back end for us. So for the project, so you may need to, and I think I have all that details in the write-up. If you're doing, you may need to add the scope information into the symbol table, the type information, since we're going to do type checking, very simple type checking. We're not going to worry about type coercion, type conversion. For instance, you're going to assign an int into a double, which is fine. Right? But if you assign a double into an int and you get a warning, okay? So we're just going to do a real simple type, checking. We're not going to worry about all these complex type rules. And depending on what you pick, even for the GUI application, you may need to save all your statements in a data structure, like into some sort of intermediate representation. So if I have, 10 drawing statements in a linked list, how does GUI work? Our GUI is just going to go through and draw them, right? So in talking about semantic analysis, I have some slides on what's known as static binding, static type checking, scope, lifetime. It's probably more information than you really need for the project. I have all kinds of information in the slides. Also, those should be covered in the concepts of programming languages classes. So as you approach any programming language, some of the questions you should ask is, how does the scoping in this language work? Is it strongly typed language? Is it weakly typed language? Okay, does it do type checking? And then there's a whole list of other questions you ask, like how does parameters get passed around, right? There's pass by value, pass by reference, pass by name, pass by, all these different ways. Some languages specify that some arguments are in and out or both. Okay, so it's like passing it by value is really just, in, but you're not actually changing the original value, and all that issues are really concepts of programming languages, not as much as compilers. So I may just touch on it a little bit. Okay, so this is a good point to take a break, because when you come back, I want to cover top-down versus, I'll show you examples. So I went through and draw little stacks, like your little stacks. So top-down versus bottom-up parsers and how they work, how they differ. I think you'll like the difference, because it really is different how that works. So that left recursion, which we spend a lot of time trying to get, remove, The bottom-up parsers, left recursions, they're just fine. In fact, they're almost all left recursive. It's because they work differently. So take a short break, about 10-minute break, come back, and we'll look through top-down versus bottom-up. Let me turn off the Hangout here.